Welcome to Chapter 32, Exchange. So far in the course, we've considered individual markets in isolation, and this is known to microeconomists as partial equilibrium analysis. But we mentioned in the very beginning of the course that consumers purchase in the course of a normal day hundreds or even thousands of products that they consume. And if we wanted to analyze the economy at a larger scale, at, dare I say, a macro-like scale, we would be considering hundreds and thousands of markets that clear simultaneously. And this is what's known to microeconomists as general equilibrium. So general equilibrium is the study of the clearing of multiple markets simultaneously, and these markets presumably interact with each other. So we've considered so far the case of complements and substitutes, and these would be examples of markets that affect one another directly. Now, in the very beginning of the course, even though we knew that consumers chose hundreds or thousands of goods to consume, Varian made the very gracious and simplifying assumption that we would only consider the market for two goods. Right? So to consider the theory of choice, we considered two goods, and we were able to apply the simplest possible mathematical techniques, but still study consumer choice. Varian's going to do the same thing for us here. He's going to define the exchange economy. So the simplifying assumptions I have here in bullets, we're going to assume again that there's two goods, and we will assume the minimal two consumers. And we will assume that each good is perfectly competitive, right? So the good can be bought and sold in a perfectly competitive market. And of course, this is something of a heroic assumption, because if you have two people trading, that's too few to really get perfectly competitive behavior. But we'll make the simplifying assumption just to make things work. And finally, we will assume that there's no production. What this means then is that the quantities of both goods that are available are only the quantities that exist in the economy before trading. Hence the name an exchange economy. Literally what happens in this simplified economy is the two consumers trade one good for the other with the other person. Now, Varian uses very clear but antiseptic type textbook notation. He assumes that we have two goods, good 1 and 2, and he assumes we have two consumers, consumer A and consumer B. And like we've done so far in the course, I'd like to give you maybe a little more entertaining example. So suppose that we have an exchange economy where SpongeBob and Patrick trade Krabby Patties and ice cream. Now, since this is an exchange economy and production is not permitted, both Krabby Patties and ice cream, the quantity of the goods consumed by SpongeBob and Patrick together must be equal to the endowment. And the new notation that Varian introduces at this point is the Greek letter omega to represent an endowment. So in the first line, you'll notice I have omega super K sub S. So that is SpongeBob's endowment of Krabby Patties. So before any trading takes place with Patrick, this is the quantity of Krabby Patties that SpongeBob has. Patrick also has an endowment of Krabby Patties. So with consumption not allowed in this simplified economy, this is the quantity of goods that exist. And the same sort of thing happens for ice cream, right? SpongeBob has an endowment of ice cream. Patrick has an endowment of ice cream. Now let there be preferences. And in this first preference map, I've proposed preferences for SpongeBob between Krabby Patties and ice cream. And just to keep things straight, I'm going to use a pink or light red color to represent SpongeBob. We're not going to introduce math just yet. That's going to come a little bit later. But you'll notice that this preference map looks very much like Cobb-Douglas style preferences. So remember, Cobb-Douglas preferences were preferences in which SpongeBob insists on having positive amounts of both ice cream and Krabby Patties. And that generates level sets or indifference curves which look like this. Krabby Patties and ice cream are imperfect substitutes, which means the indifference curves are not straight like they would be in perfect substitutes. Suppose that Patrick has the very same looking type preferences. Now, the thing that's a little bit different here is you'll notice that Patrick's origin is going to be in the northeast. So the origin up in the far northeast corner would be where SpongeBob has all the Krabby Patties and all the ice cream. So if SpongeBob has all the Krabby Patties and all the ice cream, that by definition means that Patrick has no ice cream and no Krabby Patties, which puts Patrick in the far northeast corner at his origin. So in this exchange economy, as we give one consumer more of one good, that by necessity means that we're taking that same good away from the other consumer. So as I move from Patrick's origin to the southwest, Patrick gets more Krabby Patties and ice cream, but by definition, SpongeBob gets less. Okay? So let's marry SpongeBob and Patrick's preferences together. We'll get a diagram that looks like this. What I've indicated is in the southwest corner, you'll notice there's a dot. And let that be the endowment of Krabby Patties and ice cream. So you'll notice that the endowment point that I proposed for this problem, SpongeBob has a lot of Krabby Patties, many more Krabby Patties than Patrick does. And Patrick has much more ice cream than SpongeBob does. So Patrick is heavy on ice cream, SpongeBob is heavy on Krabby Patties. I've also drawn in this diagram each consumer's weekly preferred set. So SpongeBob's weekly preferred set is in a very light red, almost a pinkish color. And the way I've constructed this is the indifference curve that goes through the endowment point. SpongeBob's weekly preferred set, just like before, is everything above this indifference curve and to the northeast. That makes SpongeBob better off. Patrick's weekly preferred set is indicated with the lightly shaded blue region. So that is the area to the southwest of Patrick's indifference curve that goes through the endowment point. So the intersection of SpongeBob's weekly preferred set and Patrick's weekly preferred set I've indicated with gray shading. And this intersection is what we would call the area of potential trade. So from the endowment point, SpongeBob will never willingly trade to a point that makes him worse off. So if SpongeBob has to be at least as well off as he was before, SpongeBob is willing to move from his endowment point to any point within his weekly preferred set. And Patrick is the same, right? Patrick is willing to move from the endowment point into any point within Patrick's weekly preferred set. The intersection of the two then indicate the areas that SpongeBob and Patrick could reach by trading with each other. Okay. Now, suppose that SpongeBob and Patrick do trade, and they trade to this point that's indicated right in the middle of the diagram. Now, you'll notice that at this point, SpongeBob's weekly preferred set and Patrick's weekly preferred set no longer overlap. They're tangent to each other. And what this tangency means then is that all gains from trade have been exhausted. And the historic way that economists would describe this is we would say that this point they've traded to is Pareto efficient. So this is a term that was introduced by this Italian economist whose last name was, of course, Pareto. He was active in the early part of last century, about 100 years ago. And this notion of Pareto efficiency says that an allocation of goods and services is considered Pareto efficient if the only way to make one consumer better off is to make the other one worse off. Okay, so the reason why this is a intuitive notion of an efficient allocation of goods in the economy, think about what that would imply if the Pareto efficiency condition were not met. If it were possible to rearrange goods to make one consumer better off without making the other consumer worse off, that would imply that the initial allocation of goods was not efficient, right? That there was efficiency to be wrung out of the marketplace. So this point in the very center of the Edgeworth box, I claim is Pareto efficient because both weakly preferred sets are tangent to each other. Now, I've indicated all the tangencies of Patrick's and SpongeBob's indifference curves with the green line. And Varian introduces this concept to us as the contract curve. This is the set of all Pareto efficient points. So if SpongeBob and Patrick were to trade with each other, what Varian tells us is that trading would get them to this set of Pareto efficient points. So rather intuitive. Now, if we think about the mathematics or the mechanism of trade with a little more detail, I would ask you first to consider the pseudo income of each consumer. Now, within this exchange economy, SpongeBob and Patrick don't have income like we thought of previously, but what we could think of as their income would be the value of their endowment at the current prices. So you'll notice the first line of each column, what I've done is I've defined the value of each of SpongeBob and Patrick's endowment at the current prices. You remember back in chapter 6 when we introduced the idea of demand. The demand function for a consumer was how much the consumer was willing to purchase of a good, and it was a function of the price of all the goods in the economy and the income that they had. Well, in the second line, you'll notice that I have, let's consider SpongeBob on the left-hand column. Notice just to the right of the equality, I have X sub S super K. So that's SpongeBob's demand for Krabby Patties. So within this exchange economy, SpongeBob's demand for Krabby Patties is purely a function of the price of Krabby Patties and the price of the price of ice cream. The reason why income isn't in SpongeBob's demand function at this point is in the previous line, SpongeBob's income within an exchange economy is just the value of his endowment. So in that sense, income, as we thought of it before, is just a function of prices. So it doesn't need to be entered into this notation. So if we take the quantity of Krabby Patties that SpongeBob wants to consume and we subtract from it SpongeBob's endowment of Krabby Patties, or how many Krabby Patties he had before trading takes place, we'll define this as SpongeBob's excess demand for Krabby Patties. So it's the quantity of Krabby Patties that SpongeBob wants to purchase beyond his endowment. So if excess demand for Krabby Patties is positive for SpongeBob, that means he wants to buy more than what he had in his endowment. If his excess demand is negative, that says that SpongeBob wants to be a seller of Krabby Patties. Okay? And we can also define SpongeBob's excess demand for ice cream in the same way. It's the difference between his demand and his endowment. And Patrick has excess demand for Krabby Patties and ice cream that are defined in an analogous manner. Okay? Now, Varian introduces a new concept at this point, aggregate excess demand. So if we add the excess demand, SpongeBob's excess demand for Krabby Patties to Patrick's excess demand for Krabby Patties, this is aggregate excess demand. So it's just the sum of the excess demand of the two consumers. So we define aggregate excess demand for both Krabby Patties and ice cream, as I have in the center, the math in the center of the slide. Now, at equilibrium prices, what should occur is that the Krabby Patties that Patrick wants to buy, the quantity that he wants to buy, must exactly equal the quantity of Krabby Patties that SpongeBob wants to sell. Right? So if the quantity of Krabby Patties that Patrick wants to buy is equal to the quantity of Krabby Patties that SpongeBob wants to sell, that means aggregate excess demand for Krabby Patties has to be zero in equilibrium. And likewise, the ice cream that SpongeBob wants to buy, the quantity of ice cream SpongeBob wants to buy at equilibrium has to exactly equal the quantity of ice cream that Patrick wants to sell. So aggregate excess demand for ice cream also has to be zero. Okay? So in this next slide, we consider what equilibrium prices would look like and disequilibrium prices. So in disequilibrium on the left, you'll notice that what happens here is that Patrick wants to buy more Krabby Patties than SpongeBob is willing to sell, right? So from these 2 points, you imagine dashed lines that went down to the horizontal axis. So moving from the endowment point over to the first one, that would be the quantity of Krabby Patties that SpongeBob is willing to sell. Patrick wants to buy a lot more Krabby Patties than SpongeBob is willing to sell. So what we have then is a shortage of Krabby Patties. And you remember from partial equilibrium analysis, if we have a shortage of a good, that drives prices up. And also, we have the same, an analogous problem with ice cream. SpongeBob wants to buy less ice cream than Patrick wants to sell. So we have a surplus of ice cream, which would tend to drive the price of ice cream down. So if the price of ice cream goes down, the price of Krabby Patties goes up. You remember that the slope of a budget line within a choice diagram was the ratio of the two prices. So the line from the endowment point projecting into the center of the Edgeworth box now becomes steeper. So as the price of Krabby Patties goes up and the price of ice cream goes down, eventually we come to this equilibrium point on the right. So at this equilibrium point, aggregate excess demand for both Krabby Patties and ice cream is equal to zero. So the quantities that each person wants to buy are exactly equal to the quantities that each person wants to sell. And we have equilibrium. Okay. So to talk more about equilibrium, we could call this a market equilibrium, or since this is a general equilibrium model, remember a general equilibrium in contrast to a partial equilibrium is where we have multiple markets simultaneously clearing. So this would be thought of as a general equilibrium or a Walrasian equilibrium. So these are all synonyms. They're different words that economists use to describe the same concept. So we'll use the highbrow one, the one on the far right. Right? The Walrasian equilibrium occurs at prices that cause the aggregate excess demand for each good to be simultaneously zero. So we have the mathematical condition that I have in the center, and Varian points out that Leon Walras was a French economist who worked at the University of Lausanne, which is a Swiss university. It's in the French-speaking part of Switzerland, and Walras was one of the pioneering economists to work in general equilibrium theory. So when you study general equilibrium, a lot of these concepts and theorems are due to Walras, and they're named after him in his honor. So we also have Walras' law, and Walras' law says that if we take the excess demand of each good and multiply that by its price, that must be identically zero. Okay, so in words, the value of aggregate excess demand must be identically zero. Varian is emphatic in pointing out to us in his text that Walras' law holds for all prices and not just equilibrium prices. So the proof of Walras' law is if for each consumer A and B, so I'm going to go back to Varian's antiseptic textbook notation. So if you want to see Varian's proof in greater detail, you can refer back to the text and it will match what we talk about here in the slides. So if each consumer A and B is on their budget constraint, right? So, and of course we know that consumers must be on their budget constraint, right? Because if preferences are monotonic, meaning that more of the good can never make you worse off, consumers will be on their budget constraints. So if consumers are on their budget constraint, then that means that the value of each individual consumer's excess demand also has to be identically zero, right? If that were not so, it would be possible to basically make endless money through arbitrage, right? So that can't be. The value of each individual consumer's excess demand is zero when they're on their budget constraint. So if we add these two identities together and factor out the prices, we get P1 times the sum of the excess demand for good 1 plus P2 times the sum of the excess demand for good 2 also must be identically equal to 0. But of course the sum of the excess demand over all the consumers is the aggregate excess demand. So this proves then that the value of aggregate excess demand must be identically zero. And that comes from the fact that each consumer must be on their budget constraint. Now, one of the more vexing problems in a PhD version of this course, actually it was the second semester of PhD microtheory, is the existence of general equilibrium, right? So when we were going over these slides earlier, you might have thought that it might be kind of hard to find prices that cause each market to simultaneously clear, right? To drive the aggregate excess demand of each good equal to 0 simultaneously. So a lot of theoretical work was done to find what are the minimal conditions necessary such that prices that support a general equilibrium exist. And Varian goes through in a fair amount of detail in the text. He derives these conditions. I'll just state them for you in the interest of time. The first necessary condition is that preferences are convex. And you remember, Varian described convex preferences way back in chapter 3 as this notion that balanced bundles are preferred to extreme bundles, right? So equilibrium will exist if preferences are convex and if the demand of each consumer is small relative to the market. So if each consumer is small relative to the market, meaning that they don't have market power, right, the ability to set or control prices, then it can be proven that prices will exist that support a general equilibrium. This leads us to the two crowning welfare theorems of general equilibrium theory. We have first, these are really intuitive and what should we say, dazzling names for these important results. We have the first welfare theorem of economics. And the first welfare theorem of economics, we could state it very succinctly that any equilibrium of a competitive market is Pareto efficient. Okay? So the proof of this, I will refer you to the textbook, to Varian chapter 32, section 10. And Varian's proof, he does a classic Varian proof. Remember, we've talked as we've gone through the course that the classic Varian proof is to suppose not, right? So what Varian does in section 10 is he supposes that we have a market equilibrium that is not Pareto efficient. And then he does a proof by contradiction. So if he supposes not, and he shows that if it's possible to make one consumer better off without making anyone else worse off, then this could not have been a competitive equilibrium to begin with, right? So if it was not an equilibrium, then we've, in essence, proved by contradiction that any equilibrium of a competitive market is Pareto efficient. So to descend from the mountaintop a little bit, the implications of the first welfare theorem would be that under the assumptions of the first welfare theorem, and Varian was actually a little bit light. You know, we made these simplifying assumptions of two goods and two consumers. So if we think about a more general exposition of general equilibrium theory, the assumptions of the first welfare theorem are, and I put them in parentheses here, there exists a perfectly competitive market for each good consumed. There are no consumption or production externalities, and each consumer or firm is small relative to the market. So if those conditions are met, then an omniscient, benevolent central planner could not engineer a Pareto improvement. So we've talked so far about an allocation being Pareto efficient, meaning that the only way to make one person better off is to make someone else worse off. A Pareto improvement is a reallocation of goods and or income that makes no agent worse off, but leaves at least one better off, right? So, what the first welfare theorem of economics tells us then is that if an omniscient, benevolent central planner existed, right? So that's a really big if. So I would very humbly assert to you that only God himself is omniscient, right? Central planners don't know everything. Government employees, government agencies don't know everything. So only God knows everything. And I would submit to you very humbly that central planners are in general not necessarily benevolent. So by benevolent, what we mean is they put your interest ahead of their own. So if it were possible for a central planner, for a government agency to know everything and to do it all for your benefit, not for their own, but for your benefit, if that were possible, that such a creature existed, they could not engineer a Pareto improvement over the outcome of a perfectly competitive market. What that means is that all a central planner can do, the only way to make one person better off is to harm someone else, to harm another person or another firm. Okay, so very important result. The second welfare theorem of economics, if all agents have convex preferences, then there will always be a set of prices such that each Pareto efficient allocation is a market equilibrium for an appropriate assignment of endowments. So you remember when we had the contract curve. So when we had SpongeBob and Patrick, there was the green contract curve that went from the southwest corner where Patrick had everything and SpongeBob had nothing, up to the northeast corner, which is Patrick's origin, where SpongeBob had everything and Patrick had nothing. All those points that were indicated in green were Pareto efficient, meaning the only way to make SpongeBob better off was to make Patrick worse off, and vice versa. Now certainly, Patrick having everything and SpongeBob having nothing is Pareto efficient, but it may not necessarily be desirable, right? So what the second welfare theorem of economics deals with is it possible for market processes to generate more desirable Pareto efficient outcomes, more desirable spots along the contract curve, right? So maybe in a society that valued equity, we decided that it would be desirable for SpongeBob and Patrick to have relatively similar amounts of consumption. So the question is it possible for market processes to generate those types of outcomes? And what the second welfare theorem tells us is that there will always exist a set of prices that will move from an appropriate endowment point to any point along the contract curve. So what this says then, the implication, it's possible for government to redistribute endowments to steer a perfectly competitive economy to any desired Pareto efficient outcome. Right? So it's theoretically possible. But this idea of redistributing endowments, if you think about the real economy, the real world as it exists, the endowment that we get might be your level of intelligence, your level of athleticism. Is it possible for the government to redistribute that? Well, it's complicated. Right? So, now, what we have considered so far, I've only given you one example, the example of SpongeBob and Patrick, who had Cobb-Douglas style preferences. And you remember the hallmark of Cobb-Douglas style preferences is that both consumers want to have some amount of each good, right? And remember that actually we showed way back in chapter 5 that consumers with Cobb Douglas preferences will spend the same proportion of their income on each good. Right? I would ask you to consider our good friends Lorraine Quiche and Shirley Sixpack. So they have very different types of preferences. So suppose that our friends Shirley Sixpack and Lorraine Quiche are staying at a hotel. Suppose they go to some corporate training event. They stay, each of them has a hotel room, and each of the rooms comes equipped with a mini bar that contains 1 6-pack of 8-ounce cans and 1 6-pack of 16-ounce cans. So that would be Shirley's endowment, and that would be Lorraine's endowment. And how would trading between Lorraine and Shirley proceed? So to consider that, I've drawn this Edgeworth box showing Lorraine and Shirley's endowment. It's that dot right in the center, and much like we did before, we could think of Shirley's weekly preferred sets. So those would be the area, that would be the area to the northeast of Shirley's red indifference curves, right? Lorraine Quiche's weekly preferred set would be the area to the southwest of her blue indifference curves. And then the intersection of those two would be the gray shaded areas. So what we could say then is that from this dot, from this endowment point in the middle, Lorraine or Shirley and Lorraine would be willing to move anywhere within this weekly within this this intersection of their two weekly preferred sets. I claim that what Shirley and Lorraine will actually do is they will go to the left edge of the box, right? That would be the area of maximum gain, or when we exhaust all possibilities, all Pareto improvements through trading, right? So if every Pareto improvement, every potential Pareto improvement is exhausted, that will happen when we're on the axis to the left, right, to the west of this box. And of course that's what the drawing says, but I claim that if we stop and think about this a little bit, this is actually quite intuitive. What is the meaning of this border on the left-hand side of the Edgeworth box? The meaning of it is that Lorraine has all the 8-ounce cans, and all the 8-ounce cans are, so Shirley trades her 8-ounce cans for 16-ounce cans from Lorraine, right? Because remember, Lorraine Quiche only drinks 8 ounces at a time, and she wastes the other 8. So Shirley, remember, thinks that a 16-ounce can is a perfect substitute for 2 8-ounce cans. So what this means then is that Shirley places a higher value on 16-ounce cans than Lorraine does. So if we envision trading between Shirley and Lorraine that exhausts all Pareto improvements will be exhausted when Shirley gets rid of all her 8-ounce cans. She's going to trade for as many 16-ounce cans as she possibly can. So in this diagram, the contract curve is indicated in green, right? So what we would say then is that Shirley wants to get all the 16-ounce cans, so that takes us from Shirley's origin upward into the northwest corner. So the northwest corner, right by the X16 label, is the point where Shirley has all the 16-ounce cans and none of the 8-ounce cans. Then at that point, the only way to make Shirley better off is to give her 8-ounce cans. So we travel along the upper boundary of the Edgeworth box until we get to Lorraine's origin up in the northeast corner, where Shirley has everything, right? So that's also a Pareto efficient point because it's efficient for Shirley to have everything and Lorraine to have nothing. It may not be equitable. Right? So if we thought about this all from Lorraine's perspective, we could generate the same thing, right? If we start from Lorraine's origin, it is efficient for Lorraine to get 8-ounce cans first, because if Lorraine values 8-ounce cans and 16-ounce cans the same, yet Shirley values 16-ounce cans more, the efficient thing is to give Lorraine initially 16-ounce cans until she has them all. And then we've moved Lorraine over into the northwest corner, and then at that point, the only way to make Lorraine better off is to give her 16-ounce cans, which sends her down the west coast, right? Okay, so the practice quiz problems. So problem 1, suppose an economy has 2 people, Charlie and Doris, and we have 2 goods, apples and bananas. Charlie has an initial endowment of 4 apples and 10 bananas. Doris has an initial endowment of 8 apples and 5 bananas. They are both Cobb Douglas. What can we say about every Pareto optimal allocation? Well, Pareto optimal allocations occur when the slope of Charlie's indifference curve is equal to the slope of Doris's indifference curve. So we just need to generate the math that causes those 2 slopes to be equal. So here's the intuition. This, of course, looks all the world like the diagram I was using for SpongeBob and Patrick trading Krabby Patties and ice cream. It is the same, right? So the Pareto efficient points are indicated by the green line, by the contract curve. Those are defined by the slopes being equal. So if I set the slopes of Charlie and Doris's indifference curves to be equal, first I have a column for Charlie, a column for Doris, okay, and I find their slopes. And then in this exchange economy, the endowment, if I add Charlie and Doris's endowments together, there are a total of 12 apples and 15 bananas. So if the apples that Charlie consumes plus the apples that Doris consumes must equal 12, and the sum of Charlie and Doris's consumption of bananas has to equal 15, then if I set those 2 slopes equal, I can substitute and say that Doris's consumption of bananas is 15 minus the bananas that Charlie consumes, right? Doris's apple consumption is 12 minus Charlie's apple consumption. And then I can work out an equality, and I get this, this condition that 12 times the number of bananas Charlie consumes must be equal to 15 times the number of apples that Charlie consumes. So this is the equation that describes the relationship between apple and banana consumption that ensures we're on the contract curve, the green line from the previous slide. Okay. I had to cover problem 6. This is one of Professor Bergstrom's, some of his absolutely best comic work. So in this particular problem, in the old intermediate micro workbook, we have Professor J. Fetid Nightsoil and Dean Foster interface. And they trade bromides and platitudes. So this is this problem is perhaps a dictionary.com moment. Night soil, you might recall, was a term, a genteel term from 19th century England before the advent of indoor plumbing. Before people had indoor potties, what people would do is they would have in their bedroom what was called a chamber pot. So if you woke up in the middle of the night and had to go to the bathroom, rather than use the outdoor facilities, you would go in the chamber pot, so you didn't have to leave the warmth of your bedroom. And then in the morning, what you removed from your chamber pot was called night soil. Okay, so we have Professor Night Soil. A bromide and a platitude, these are actually synonyms. As I recall, the dictionary.com definition for both is a trite saying that is expressed in such a way that makes it seem like it is a fresh, new insight, right? But these are old sayings. So imagine sayings like, "A stitch in time saves 9," or "A penny saved is a penny earned." So you can imagine Professor Night Soil and Dean Interface. Of course, they want to have clever things to say to impress people and show how smart they are, but they lack creativity. They can't make any more bromides or platitudes, so they're reduced to trading with each other for them. So this problem is just a work of art. Well, anyway, both Professor Night Soil and Dean Interface have quasi-linear utility. And remember, quasi-linear utility, you're nonlinear in one good and you're linear in the other good. So both of them are nonlinear in platitudes. They're linear in bromides. So what this implies then is that at market prices, each of them has a desired quantity of platitudes, right? So both of them care deeply about the quantity of platitudes, and as they become wealthier, they don't want more platitudes. They will expend their extra income on more bromides. So in this problem, we say at any Pareto efficient allocation where both persons consume positive amounts of both goods, what has to happen? Well, so if we have quasi-linear utility, it's possible to have corner solutions where the consumer buys all of one good and none of the other. So we're told, we're asked in this question, how to describe the points where they each want some quantity of each good. So that occurs where the slopes of their indifference curves are equal. So the intuition, this was a ghastly complicated diagram to draw. I don't even want to tell you how much time I spent getting this one right. But so as before, we have the contract curve, which are the Pareto efficient points. They're indicated by the green line. So if we start from Professor Night Soil's origin, we go along the horizontal axis until we get to the desired amount of platitudes that Night Soil wants. And then as Night Soil becomes wealthier, he will get additional bromides, but he doesn't want any more platitudes. And then we get up to the top, and then the only way to make Night Soil better off at that point, after he has all the bromides, is to give him more platitudes. We have the same story if we start from Interface's origin, right? So we give Interface more platitude, we give him platitudes until he gets to his desired amount, and then Interface is made better off by giving him more bromides. So and remember the question asked, what must be true for equilibria where both academics consume some of each good. Well, those are the points where the slopes of the indifference curves are equal. So if we think about the math of this problem, we need to find the slope of Professor Knight's soils indifference curves, and that's on the left, and the slope of Dean Interface's indifference curves, and that's on the right. So I get their slopes and I set them equal, and I'll do actually very much like what I did with Charlie and Doris in the previous problem. I'll set them equal, but I know that there are 35 platitudes given the endowments. So what that means then is that that night soil's consumption of platitudes is 35 minus what Interface consumes. So I make that substitution in, and I find that this equilibrium is characterized by Dean Interface having 7 platitudes and Professor Knight's soil having the remainder, which would be 28. Okay.